In this video, in order to get a better insight of these power series applications, let's start with this result and doing some examples. So let's start with the simple function. Now the function is the same as before, that is ex, but now let's change the center to 2, right? So the center in this case is equal to 2, but remember I mentioned no matter what center you use, the formula will be the same, right? So now that means you can even write this function also as a power series where the coefficients are given like this, right? So in that case, now you can see if fx is equal to e to the power x, the derivatives of fx, all the derivatives will be the same because the derivative of ex is ex itself, right? So now if all the derivatives are the same, is ex, like what I mean by this notation is the nth derivative of fx, right? And that is also is equal to e to the power x, right? That means if you evaluate the nth derivative at 2, it will be equal to e to the power 2, right? In other words, Cn, which is equal to the nth derivative, remember this is not the nth power but the nth derivative evaluated at the center divided by n factorial, right? And that is equal to e to the power 2 divided by n factorial. So by substituting this corresponding Cn values in our power series notation, you can obtain the power series of this same function evaluated at center 2, right? Okay. And how about the radius of convergence of this series? Now remember, in the previous video, we already evaluated that the radius of convergence, this color is not that good. Okay, let's choose light. Yeah, this works. So we in the previous video we evaluated the e to the power x function centered at 0, right? And then we saw that its radius of convergence is equal to infinity. That means for any value of the real number set, you can write it as a power, for any real number, this relationship is true, right? And that means if you choose whatever the real number you prefer, now say this is the power series evaluated at 2, right? Now let's have this as 0 and this as 2, okay? But when you consider the power series at 0, we already knew that for all these real numbers, this relationship will be true, right? And that is, if you choose any number from here, it can be expressed as a series, as a value of this series, the value of this series at that specific point can be visualized as the function evaluated at that particular point. So basically, for all these values, this series equation holds true. So it kind of indirectly imply that this series representation will also be true for all these real numbers, because now this is not a proof but a kind of a basic idea that you should have in your mind when you are dealing with this radii of convergence, right? Now this series was true for all these real numbers, so now this is also a series, a power series with a different center, right? So now since this holds true for all these real numbers, it will indirectly kind of imply that this series will also be true throughout the real number set. But if you need to write a exact proof, you just have to go through the ratio test and you can directly evaluate the radius of convergence. That's fine. Okay, so this is just a kind of a idea that you can obtain from this known result. Now you don't have to remember all these formulas, okay, but this is a formula that you must remember: the power series of e to the power x evaluated at 0, right? Now now the reason for taking this example is I wanted to show you how this relationship can be used to obtain the power series expressions, right? Let's try another example. Now this time it is the function sin x at this center, right? Then again, in order to write it as a power series, now here the center is 0, so it's basically sigma cn x to the power n, right? So now we need to evaluate these cn coefficients, and we have our familiar formula and we can directly evaluate the derivatives. But now remember, in this case we were able to calculate all the derivatives at once, because no matter what derivative you take, it was always e to the power 2. But when it comes to sin x, it is not that easy, right? So if you just compute a couple of derivatives, you can see that the first 4 derivatives are different to each other, but the now before going into that, I need to mention one more thing. Now when it comes to this one, right, here the indexing starts at 0, right? So C0 is also included in this equation. Then what do we mean by this one? So if we need to calculate C0, we need to calculate this term, right? The 0 factorial is equal to 1. That is, by definition, 0 factorial is equal to 1. And what about this one? Now usually this represents the nth derivative, but what do we mean by the 0th derivative? That is basically the normal function, right, without taking any derivatives, right? So this is basically the function evaluated at a. So keep this also in your mind, right? Now let's come back to the derivatives of the function. So here this is the f0th derivative of f, right? Okay, so if you compute these 4 things, they will be different to one another, but starting from the 4th derivative, you can see it is equal to sin x. So that means the 5th derivative will be cos x, 6th will be this one, 7th will be this one. Once again, the 8th will be this one, 9, 10, 11, and then 12, 13, 14, 15, 16th derivative, 17th derivative, 18th derivative, 19th derivative, 20th derivative. So likewise, it repeats 4 by 4 sets, like it repeats as 4 by 4 sets, right? So these numbers which are evaluated at 0, because the center is 0, so these coefficients will also repeat in the same manner. See, you will get zeros also, right? Hence if you write down the terms, you can see that all these even derivatives, now 0 is also even, all these even numbered derivatives are 0. So that means all the even powers has even numbered derivatives as coefficients, right? So all the even powers will get cancelled out, and then you will get the odd powers remaining, right? So accordingly, if you write down the corresponding Cn terms, now these are the Cn terms, that means the coefficients of our power series, this one where a is equal to 0 in that case, in our specific case. So if you write down the corresponding terms, you can see that all the even powers vanishes out, remaining with only the odd powers, and the plus minus nature will interchange, right? And this is important, and this is a formula that you should remember. It's not difficult at all. What you should have in mind is, for sin x, you will only have odd numbered powers, and the plus minus nature will interchange one after the other. And the way that you can write this addition of infinite number of terms is by this method, right? I mean, you can write it as a series notation through this sigma notation, and this negative 1 to the power n represents the plus minus nature. You should be careful to select the correct number as the power, right? You can even put it as n. Sometimes n plus 1 will work, but if you use n plus 1 here, you will, since the indexing starts at 0, and if you put n plus 1 here, you will get negative number, you will get a negative coefficient as the first term, but it is not so, right? So you should carefully check your sigma notation after you write that down, right? And the most important thing you should remember is, for sin x, you will get odd terms with pluses and minuses as coefficients. I mean, they come as coefficients interchangeably, right? And in the denominator, you will get the factorials of these corresponding powers, right? And once you get this one, you can directly differentiate this equation throughout and obtain the power series of cosine x, right? Or else, if you don't have this, you can redo this calculation for cosine x, right? Then you can see, for cosine x, all the odd powers will vanish and you will have the even powers only. So it will start at 1. See here, you have like it starts at x to the power 1, but here it starts at x to the power 0, which is a even power. And once again, the plus minus nature will repeat one after the other. So these two are very important formulas that you should have in your mind. Okay, right? So, and also you can do some simple manipulations with these power series notations, right? If you have this relationship, then you can directly obtain the power series of x times cosine x. You just have to multiply this equation by x. So you will get x here, and then you can take that x inside. So you will have x to the power 2n plus 1, because you will be multiplying this term with x to the power 1. So by computing these powers, you will get 2 to the power 1 as the power of x, and everything else will remain the same, right? So now the key point I want to highlight here is about using this relationship that we obtained from this initial result, right? And how about this one? Okay, now for this one, it is the same function as this one, but evaluated at pi by 3. So the only difference you have to do is you just have to you just have to evaluate the coefficients of sigma cn x minus a. Now here the center is pi by 3, right, to the power n equals 0 to infinity, and you just have to do the same calculation here but according to the specific center, right? Then you can see that the coefficients will be like this, and when you write down the terms it will be something like this. It's a bit messier, and if you try a little bit hard, you might be able to come up with the general term like this, but it's not that important, right? You don't have to remember any of these stuffs, but you just have to be familiar with these calculations. If we are to find a power series, what you have to do is you just have to first of all you just have to realize that it is this relationship that you need, and then from this result you will be able to calculate the required coefficients. And once you calculate the coefficients, now in all these things except for this last one, we were able to find a general term for those coefficients. Then only we will be able to write it as a sigma notation, right? Otherwise we won't be able to do it. Now see here, it's not that easy to find a general term for the cnth term, right? So we just leave it like that. But in these cases it's easy to find a general term for the cnth coefficient, hence we can write it with the sigma notation. And then once you write it down with the sigma notation, you can even differentiate as well as do some simple arithmetic manipulations like this in order to obtain the power series representations for different functions. And in the next video I will introduce you to some more definitions and probably some graphs.